Welcome to our deep dive on black holes. We're going to be exploring these cosmic enigmas using the research that you've provided. And, they're considered one of the strangest things in existence. Have you ever wondered, like, what would happen if you fell into one?
Black holes, they really challenge our understanding of how the universe works. They push the limits of physics and make us ask some truly fundamental questions.
Yeah, the source material starts by addressing some really simple questions. Where do they come from? What are they like? And, of course, the big one, what happens if you fall into one?
And it's interesting to note that they aren't random occurrences. They're the final stage in the life of certain stars.
So it all starts with a massive cloud of gas, and it collapses under its own gravity. This forms a star. And that star then spends most of its life balancing between the inward pull of gravity and the outward push of nuclear fusion. It's like a cosmic tug of war.
And this fusion process is crucial. It's how stars create energy by fusing lighter elements into heavier ones. But this process hits a snag when a star starts producing iron.
Right, the source mentions this iron problem. Fusing iron doesn't release energy like fusing lighter elements.
Exactly. Without that outward energy, gravity wins the tug of war. The star's core collapses. And this leads to a supernova.
So imagine a massive star exploding.
It's one of the most spectacular events in the universe. And it scatters elements across the cosmos. Those scattered elements become the building blocks of planets and even life itself.
So from the remnants of this explosion, two things can happen. A super-dense neutron star can form.
Or, if the original star was massive enough, a black hole is born.
So now we have incredibly dense objects. What makes a black hole so black?
The answer lies in the event horizon. Imagine a waterfall. Once you go over the edge, there's no swimming back upstream. The event horizon is kind of like that, but for light and matter. It's a boundary around a black hole where gravity is so strong that nothing, not even light, can escape.
The source describes it as needing to travel faster than the speed of light to escape, which we know is impossible.
Exactly. Because no light can escape, we can't see black holes directly. That's why they appear black. However, we can observe their effects on the matter surrounding them.
So there's this invisible boundary. And beyond that, we have the black hole itself. But what exactly is inside?
It's not just empty space. At the center of a black hole is something called a singularity.
And a singularity is?
A point of infinite density where all the matter of the black hole is concentrated. It's like taking all the mass of a star and crushing it into a single point.
The source describes it as having no surface or volume and compares defining a singularity to dividing by zero, essentially saying our current understanding of physics just doesn't work there.
It's a point where our current laws of physics break down. It's one of the biggest mysteries in science.
So we have black holes being incredibly dense. They have a point of no return. And a center that defies our understanding of physics. There's a common image of black holes as giant cosmic vacuum cleaners sucking up everything in sight. Is that really true?
That's a misconception. The source material addresses this directly. If our sun were suddenly replaced by a black hole of the same mass, the Earth's orbit wouldn't change. We wouldn't be sucked in.
Well, that's good to know, though the source does point out that we'd freeze to death without the sun's warmth. But black holes don't actively seek out matter to consume.
Precisely. They have a gravitational pull just like any other object with mass. It's their extreme density that makes their gravity so powerful near the event horizon.
So they're not cosmic vacuum cleaners. What about all the talk about time being warped near black holes? Is that actually a thing?
Absolutely. The way black holes warp space and time is a direct consequence of their immense gravity.
So let's change perspectives for a moment. The source describes how, from an outside observer's point of view, someone approaching a black hole would appear to slow down, freeze, and then just fade away.
That's not just an optical illusion. Time actually slows down for the object approaching the black hole relative to someone observing from a distance. It's one of the most dramatic demonstrations of Einstein's theory of general relativity.
So the source material says if you were the one falling into the black hole, you could watch the rest of the universe in fast forward, kind of like seeing into the future.
It challenges our usual understanding of time as a constant universal flow. Near a black hole, time becomes relative, dependent on your frame of reference.
Okay, so let's talk about what happens to the stuff that actually falls into a black hole. Is it just crushed into oblivion?
There are a couple of main theories about that.
Let's hear them.
One theory is spaghettification. As you approach the black hole, you'd be stretched out like a noodle.
The source paints a pretty vivid picture of this. It says the amount of gravity would pull your feet with a much stronger force than your head, stretching you out into a long, thin strand. You'd eventually be reduced to a stream of plasma, just one atom wide, potentially stretching for miles.
Another theory is the firewall theory. It proposes that instead of being stretched out, you'd be instantly incinerated upon reaching the event horizon by a region of intense energy.
So the source seems to suggest the size of the black hole determines which fate you'd meet. Smaller black holes would destroy you before reaching the event horizon, while larger ones might allow you to pass through before meeting your demise.
That's right. The size and mass of a black hole are key factors in determining what happens to anything that gets too close. And speaking of size, black holes come in different varieties.
So the source mentions categories like stellar mass and supermassive black holes. Can you tell us a bit more about those?
Stellar mass black holes are formed from collapsed massive stars. They're usually a few times the mass of our sun. Incredibly dense but relatively small in cosmic terms.
And what about supermassive black holes?
These are the giants, the ones that live at the centers of galaxies, including our own Milky Way. They can have masses billions of times greater than our sun. The source even gives an example, S50014 plus 81, a black hole with 40 billion times the mass of our sun.
And how big is it?
It has a diameter of 236.7 billion kilometers. To put that into perspective, if it were at the center of our solar system, its event horizon would extend beyond the orbit of Pluto.
So that's hard to even imagine. If nothing can escape a black hole, how do we even know about objects like S50014 plus 81?
We detect black holes indirectly by observing their effects on the matter around them. For example, we see stars orbiting incredibly fast around seemingly empty points in space.
Ah, so we're seeing the gravitational influence of something massive, even though we can't see the object itself.
Exactly. By studying those effects, we can infer the presence and properties of black holes, even those billions of light years away.
So this makes black holes seem almost invincible, right? They exist forever, swallowing up matter and warping space-time. Is that the case?
Not quite. Even black holes have a lifespan, though, incredibly long.
How does a black hole die?
It happens through a phenomenon called Hawking radiation.
I've heard of that term, but don't fully understand it.
Hawking radiation is a complex topic, but the core idea is this. Black holes slowly lose energy, which seems to contradict the idea that nothing can escape them.
So even these seemingly invincible objects aren't eternal?
Not in the grand scheme of things. The source emphasizes that this evaporation process is incredibly slow, especially for supermassive black holes. We're talking timescales longer than the current age of the universe.
What happens when a black hole finally evaporates completely?
The source describes it as an incredibly energetic event. It releases a burst of energy equivalent to billions of nuclear bombs.
So it sounds like this grand finale is so far in the future that, as the source puts it, nobody will be around to witness it.
It is quite a cosmic irony. These objects that warp time and defy our understanding of physics eventually succumb to the same forces of entropy and decay as everything else in the universe.
That was a fascinating look at the world of black holes.
It was, and we've only scratched the surface. There's still so much we don't know about them. Welcome back to our depth dive into the world of black holes. When we left off, we were discussing how even these seemingly invincible objects have a lifespan.
Right, and it really makes you wonder about the long-term fate of the universe if everything eventually succumbs to entropy and decay. But before we get too existential, let's go back to something you mentioned earlier about how we can detect black holes indirectly by observing their effects on their surroundings. Can you expand on that?
Sure. One compelling piece of evidence comes from binary star systems, where one star is invisible, yet exerts a powerful gravitational pull on its visible companion.
So it's like watching a dance where you can only see one of the partners. You know someone must be leading even though you can't see them.
That's a great way to put it. Astronomers can measure the speed and orbit of the visible star and use those observations to calculate the mass of its invisible partner. If that mass is high enough, it can only be a black hole.
So we're using gravity as a cosmic scale to weigh the invisible object.
Exactly. We can also see the effects of black holes on a larger scale. At the center of many galaxies, including our own Milky Way, we observe a swirling disk of hot gas and stars orbiting a supermassive black hole.
So even though we can't see the supermassive black hole directly, we can infer its presence based on the movements of stars and gas around it.
That's right, there's another sign. Black holes can act as powerful cosmic engines, driving jets of incredibly hot gas and radiation out into space.
Wait, so if a black hole pulls everything in, how can it also shoot things out?
It seems paradoxical, but here's how it works. As matter spirals inward towards a black hole, it forms a swirling disk called an accretion disk. Friction in this disk heats the gas to millions of degrees, causing it to emit intense radiation.
So it's like a cosmic whirlpool, but with superheated gas instead of water.
A good analogy. Some of that superheated gas, guided by magnetic fields, is channeled away from the black hole's event horizon and blasted out into space as powerful jets.
So black holes aren't just cosmic drains, they're also sources of immense energy.
Precisely. And these jets can extend for millions of light years, influencing the evolution of entire galaxies.
Wow. Considering how dramatically black holes can warp space-time, Could they be used for things like time travel or interstellar travel?
That takes us into the realm of speculation and science fiction. While black holes offer some intriguing possibilities, we're still very far from understanding how to harness their properties for those purposes.
Right, of course. It's always tempting to let our imaginations run wild, but it's important to stay grounded in what we know.
Of course, but that doesn't mean we shouldn't explore these possibilities through thought experiments and theoretical models.
So hypothetically speaking, if we could safely navigate near a black hole, what kind of time-bending adventures could we have?
According to Einstein's theory of general relativity, time slows down in strong gravitational fields. So if you were to orbit close to a black hole's event horizon, time would pass more slowly for you than for someone observing from a distance.
So you'd essentially be traveling into the future, spend a year orbiting a black hole, and return to Earth to find centuries have passed.
Theoretically, yes, but getting close enough to a black hole to experience significant time dilation would be incredibly dangerous, and the technological challenges of such a journey would be immense.
Yeah, our current spaceships wouldn't be equipped for a black hole sightseeing tour. What about using black holes as portals to other parts of the universe? I've heard about wormholes.
Wormholes are a fascinating theoretical concept. They're essentially shortcuts through space-time that could connect distant points in the universe.
Like a cosmic tunnel. You enter one end and pop out the other end, potentially millions of light years away.
Exactly. However, as far as we know, wormholes are purely hypothetical. We haven't observed any direct evidence for their existence.
But the idea is that black holes, with their extreme warping of space-time, could potentially play a role in creating or stabilizing wormholes.
That's one idea physicists are exploring. Even if wormholes do exist, there's no guarantee they'd be traversable or lead where we want to go.
It sounds like a cosmic lottery ticket with very uncertain outcomes.
Indeed. And the conditions inside a wormhole could be incredibly chaotic and unstable, making survival unlikely.
So it seems like we're still in the very early stages of understanding the true potential of black holes.
Black hole research is one of the most active and exciting areas of modern astrophysics. Every new discovery raises more questions, pushing the boundaries of our knowledge and challenging our understanding of the universe.
Well, this deep dive is creating a real sense of awe and wonder. Black holes are truly mind-bending objects.
They are. And as we continue to explore them, we're likely to uncover even more secrets about the universe and our place within it.
Welcome back to the final part of our black hole deep dive. It's been quite a journey, exploring everything from their formation to the possibilities of time travel and wormholes. But let's bring things back down to Earth, or at least try to.
Right. It is important to remember that while we've been discussing the more theoretical aspects of black holes, there's a lot of really exciting observational work happening as well.
You mentioned the Event Horizon Telescope earlier. It kind of sounds like something out of science fiction, but it's a real thing, right?
It is. The Event Horizon Telescope, or EHT, is not a single telescope, but actually a network of radio telescopes spread across the globe. They work together to create, essentially, a virtual telescope the size of Earth.
Wow, that's a pretty remarkable level of scientific collaboration. What are they trying to observe with such a powerful instrument?
The EHT was designed to capture the first ever image of a black hole's event horizon. And in 2019, they accomplished this. They revealed the shadow of the supermassive black hole at the center of the galaxy N87.
Yeah, I remember seeing that image making headlines everywhere. It looked like a blurry orange donut.
Ha, that's a good description. The bright ring is the light from the accretion disk, the superheated gas swirling around the black hole being bent by intense gravity. The dark center is the shadow of the event horizon, the point of no return.
It's amazing that we can actually see that boundary, the place where gravity becomes so strong that not even light can escape.
It was a groundbreaking achievement, providing the first direct visual confirmation of Einstein's theory of general relativity. It also gave us a glimpse into one of the most extreme environments in the cosmos.
What's next for the EHT? Are they planning to image other black holes?
The EHT collaboration is ongoing, and they're constantly working to improve the resolution and sensitivity of their observations. One of their next targets is Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy.
That's exciting. It feels like we're just beginning to understand what we can learn from these enigmatic objects.
That's the nature of science. Every answer leads to more questions, pushing us to explore further into the mysteries of the universe.
Well, we've reached the end of our black hole deep dive. We've covered so much ground, from the life cycle of stars to the mind-bending physics of space-time to the incredible observations that are revealing the secrets of these cosmic enigmas.
We've explored black holes from both theoretical and observational perspectives. One thing is clear, they will continue to fascinate and inspire scientific inquiry for generations to come.
Who knows what discoveries await us in the future? Perhaps one day we'll unlock the secrets of time travel, or harness the power of black holes for interstellar travel. But until then, we can continue to marvel at these objects. They push the boundaries of our understanding and remind us of the vastness and wonder of the universe. Thanks for joining us on this deep dive into the world of black holes. Keep looking up and never stop exploring.